Right, so these are the things that we've gone through in the webinars off-site, and I'm going to go through them again and talk about how you would revise these things. And we're going to put out a multiple choice quiz so that you can test your revision. And one of the first things that I said it would be a good idea to revise are the units for physics. So I've got those on the screen now. The ones that I would start with are the ones that are multicolored down the left-hand side. And then if you're able to do some of the other ones. Now, what people often do is look at it and go, well, that's 34 things. I can't remember 34 things. That's ridiculous. I'm never going to be able to do that. I would never try and learn a long list like that all at once. If, on the other hand, you'd said, I'm going to learn numbers 1 to 6 this week, I should have imagined most people would say, okay, well, that looks a little bit more manageable. I think I can do that. If you feel a little bit more confident and you think, well, actually, I can do 1 to 10 in a week, that's okay. Or maybe you look at it and go, well, look, number 5 to 15, they're all really just 2 different measurements, and I'm just going to learn all of those ones. And what you need to do is take this piece of this sheet here. Now, it might be that you take it as a print off, or you might write them out. And what you need to do then is to look at them and then try and cover them and try and write them out yourself, because that act of trying to remember them is what will make it stick in your head for the future. And then you look to see which ones you got right, have a double look at the ones that you got wrong, add them into your list, and then go away and come back half an hour later and do the same thing. You won't remember them the first time or the second or the third, but if you do that 10 times over a week, maybe even 20 times over a week, but remember, each time it only takes a minute or so. So we're really looking at 25 minutes of work. You'll find that you should be able to remember, depending on how you find it, 5 or 6 or 10, or if you're really, really pushing it, 15. And if you look at it like that, it makes it much easier to start to remember some of these things. So now I want to go back to one of the first webinars that we did and just revise some of those facts. So one of our first things was when we were talking about waves. So here are the things that you need to revise for waves. So the first thing that you need to have a look at are transverse waves. You need to recognize that the one that looks like that, is a transverse wave. And there are some words we need to know. So oscillations. The oscillation is the vibration or the movement. And in a transverse wave, the oscillations, the particles here, if we looked at a wave in the sea, they're going up and down, but the wave is going across my screen. So they are at right angles to the direction of the wave, or the energy transfer. It would really help if you can remember this phrase. The oscillations are at right angles to the energy transfer. But if you can just remember that the wave goes up, the parts of the wave go up and down, but the wave itself is moving along like that, and you're able to describe that. You then need to know some names. You need to know that the top of the wave is called the peak or the crest, and the bottom is called the trough. So that's our first wave, a transverse wave. You'd need to know examples of this. And the best examples that you could use are light waves, all of the electromagnetic waves, but light is one that's easy to remember, and waves in the sea. These are both transverse waves. So those are good examples. The next one's a bit harder. I accept that. They are called longitudinal waves. And the reason they're called longitudinal waves is that all the movement is along the same line, okay? Because it goes along like that, longitudinal waves. And that means that our vibrations, our oscillations, are parallel to the energy transfer because they're all on the same line. So they still vibrate, they still go backwards and forwards, but they're all on the same line, longitudinal. And the best example of that is a sound wave. The particles in the air are slamming into each other and moving the next ones along. So they're going along like that, and the wave is going along like that because it's a longitudinal wave. Difficult words. Well, let me know. Where it's all squashed up, where the particles are squashed up with each other, we call that a compression. That's easy to remember because compressed things are squashed. What's trickier is where they're pulled apart, rarefactions. And the way that I remember it is where it's pulled apart, the particles are rare. And so it's a rarefaction because the particles have been pulled apart. So they're rare. Where the particles are rare, in the middle, it's a rarefaction. Little things like that, trying to use the words is remember dual coding. So we're trying to think of a different way of remembering it rather than just having to remember the word rarefaction, which is an odd word that we don't use day to day, but rare is a word that we use day to day. So it's a bit easier to remember. So the first two things about waves, we've got transverse waves and we've got longitudinal waves. That's the first thing that we've tried to remember. And then a mechanical wave. So any wave can be a mechanical wave. And if it's a mechanical wave, that means that there are some actual particles moving. Let's look at examples. Well, we said transverse waves could be the waves in the sea. And in the sea, the water is actually moving. We can see the water going up and down like this. The wave goes along, but the water just goes up and down. Okay, we can see it moving. Sound waves, we've just said that we know air particles slam into each other to make sound waves. So a mechanical wave is one where particles are actually moving. And those are our two examples. We need to know a little bit more. So now we're going to talk about some details of waves. So here is a transverse wave that we've drawn here, and then we can put some labels on it. So the wavelength, okay, which is the distance between the two tops of the wave there, or we could do the two bottoms of the wave, or we could do the two middles. But the distance between 2 points the same on the wave is called the wavelength. That's nice and easy. And it's measured in meters normally. Nice and easy. Amplitude is the height of the wave from the middle. Not the total height, height from the middle. And in sound waves, the amplitude determines the sound amplifier. The bigger it is, the more you've amplified the sound. And then the one that's a little bit odder is frequency. So that's how many waves you get per second. So if this picture is 1 second long, we have 7 waves. So the frequency is 7. There are 7 waves per second. And we measure that in hertz, like the rental car. Exactly like the car rental company, hertz. And that leads us on to, hopefully, a wave equation, is it? Wave calculation. Right. Now, you don't get given this equation. However, most of the time in the foundation paper, they will. That doesn't mean they always will. You shouldn't bank on it. This is one of the easiest ones to remember. Wave velocity is frequency times wavelength. And no one that I teach wavelength forgets it. And the reason is that silly upside down y is called a lambda. All right, so lambda, this is my favorite equation because it's got my name in it. Velocity, frequency, wavelength. And that lets you calculate either the wavelength, or we can rearrange it by putting it into a triangle. Let's see if I got a triangle here. No, I haven't. So to do a triangle, we put these two on the bottom, we put this one on the top, and we cover whatever it is that we're trying to find and do the rest. So things to revise so far: learn some units. Second, learn transverse and longitudinal waves. Try and label a wave, try and learn that equation. And again, don't do all of this at once and say, right, I'm doing 2 hours of science revision. It's melting my brain, I can't do it. Say, right, I'm going to learn that equation today. Nothing else, that's all I'm going to do. Learn that equation and the units and the words for it. I'm just going to learn that. Now, if you do that over and over, so come back to it for 2 or 3 minutes, 4 times during the day, you will probably remember it by the end of the day. And then a couple of days later, try it again, and it'll go deeper and deeper into your memory. If you're learning transverse and longitudinal waves, draw them out today, maybe, have a look at them, come back to them tomorrow and see if you can draw them out without looking. Correct yourself, do that a couple of times. Don't try and sit down with all of this and remember. I couldn't sit down with all of this and remember it at once if it was something I didn't know. It doesn't work like that. You need to do it in little chunks often. All right, so that is one set of webinar things that we went through. The next thing that we had a look at was magnetism and electromagnets. So we had a look at this. So what would you need to revise from this? Well, I think the first thing that's important is knowing what magnets do. Now, most people are quite good at this. So if you put two like poles, two north poles together, they try and push apart and go in a different direction. We call that repel. If they're opposite poles, everyone remembers this one because opposites attract. So that's nice and easy. The magnetic materials, the ones that you need to remember, iron, steel, and nickel. Permanent means always. So a permanent magnet is always a magnet. And induce, remember, it means we can make it a magnet. But usually we're talking about electromagnets. So by turning the electricity on, we can induce a magnetic field. And when we switch it off, it goes away again. Okay. And then we looked at how we would draw a magnetic field, and I showed you some e-chalk slides, remembering that we always draw the magnetic field coming out of north with an arrow and going into south. Then we started to talk more about electromagnets. Now, this is a little bit more important. If you run an electric current through a wire, any wire, you create a small magnetic field. You don't need to know why. It just happens. If you roll that wire up into a coil, you can concentrate the magnetic field. And if you look there, there are some iron filings that have been sprinkled around that coil, that wire, and you can see they've lined up into the magnetic field. It's much stronger because they've all been added together by wrapping it round. And we call that coil of wire a solenoid. And it's useful to us because if we stick a piece of a metal that can be magnetized in the middle, like an iron nail, we can make an electromagnet. We turn the solenoid on, the wire on, and the nail becomes a magnet. It is induced to have a magnetic field, and we can pick things up with it. You've probably done something like this, maybe lower down in the school, and you try to pick up paper clips. I would have thought that's what people normally do. Although some people just see if they can make the wire really hot and burn their fingers. Now, electromagnets are brilliant because they're so useful to us, because we can turn them off and on. Now, in films, loads of people, when I ask for a use of electromagnets, say that thing that comes down, picks up a car, moves it and drops it. Brilliant. That's a good example. But there are some other examples. We're going to look at them in a minute. Now, we can make them stronger. We put more coils on, better core, or a core if it hasn't got one, and increase the current. 3 C's. Coil, core, current. You need to revise that. So you need to know what an electromagnet is. Okay, I'm going to leave that at that one. So things to revise so far. Units, longitudinal transverse wave, label a wave, wave equation, how to make an electromagnet, and some of the words around magnets: induce, permanent, repel, attract. Okay, so if you get that far, you're doing pretty well. Then there is the last piece of revision. I told you it wasn't going to be too long today. Now, this is the last thing that we looked at. Okay, so here what you're revising is the words. You need to know what a vector and a scalar mean. These are things where you just have to learn the word. So if we go, so a scalar has only got a magnitude. And remember, we said that magnitude means size. So, for example, we could talk about mass. You know, I've got a box of crunchy nut cornflakes. I don't know why that came into my head. I keep going on about crunchy nut cornflakes in webinars. I do love them. I've got a box of crunchy nut cornflakes downstairs. On the side, it says 1 kilogram. That's the mass. That's how many crunchy nut cornflakes I've got inside. I've got 1 kilogram. There's no direction to that. That's just how much there is. So mass has only got a magnitude. Speed. If you're going in your car and you look at the speedometer and it says 30 miles an hour, that tells you how quickly you're covering the ground. It doesn't tell you which direction you're going in. It just says that's how quickly you're going. Just got a size, a magnitude. A vector is something that has a direction. So if we talk about the force of gravity acting on me, that creates my weight, and that has got a direction because it's down onto the earth. My weight doesn't go anywhere else, it goes down, and that's how I can measure it by stepping on scales. Velocity has got a direction. Remember, velocity is speed with a direction. It could be 30 miles an hour north or 30 miles an hour to the right, but it always has a direction on it. We often show that by putting an arrow. Let's have a look. So Here is an arrow representing the acceleration of this plane, not its speed, its acceleration. And we draw a vector arrow. And these arrows have to be in proportion. So the bottom one has more acceleration. You can tell that it's got a bigger arrow. But the mass has no arrow. We just write that on the plane. So in a diagram, we just put that on. Bottom one has more mass. No arrow, no direction. If we are going to make the acceleration double, we have to make sure our arrow is exactly double in length. This is somewhere where students who are doing the foundation paper often pick up lots and lots of marks because they take more time than students that are doing the higher paper, think they know it all and they're going really quickly, and they don't bother to measure the arrows. If you are drawing arrows or you're asked about the arrows, measure them with a ruler and then you know everything. If it's twice as long, it's twice as much. If it's 3 times as long, it's 3 times as much. Make sure your arrows, your vectors, are drawn nicely. Okay, very, very important. So let's move on. So there's some common ones. I wouldn't suggest that you have to memorize them all. Have a look at a few, but you just need to think, can I draw an arrow to show which way this is going for temperature? Well, clearly not. I can't draw an arrow for temperature. It's either 20 degrees or it's not. So if you can't draw an arrow, it's a scalar quantity. Okay, have a little think about that. Distance, 30 meters. Can I draw a direction for something being 30 meters long? No. So it's clearly not a vector. However, acceleration, can I draw an arrow to show which way something's accelerating? Yes, that means it must be a vector. For forces, can I show which way something is being pushed or pulled? Yes, so it's got an arrow. Magnetic fields, we talked about them a minute ago with the arrow coming out of north. It's got an arrow on it, means it's a vector. If you can do an arrow, that means it's a vector. So those are some questions to practice. And then we talked a little bit about forces. Now, things to remember here. Let's go through. First of all is if you've learned your units, you're good already because you know that forces are measured in newtons and that they're either pushes or pulls, and they either make things change shape or accelerate or change direction. Okay, so those are the things that they can do. You've had a good idea. Again, you don't have to learn all of these. You just need to learn the idea. We've got 2 types. We've got contact forces. They have to be touching. Friction. I can't have any friction unless my hands are actually touching each other. No friction there. I'm just moving. Friction. Okay. Non-contact forces. If I hold my phone in the air and let go of it, it will still fall to the ground. I'm not going to do it. I might do it with a pencil. If I hold it up in the air and I let go, it still falls to the ground because gravity doesn't need to be touching something to pull it down. Okay, contact, non-contact. So these are our contact forces. Air resistance. Unless you're touching some air, you can't have air resistance. Buoyancy. Unless you're touching some water, it can't be pushing you upwards, and so on. Non-contact forces. Okay, those are ones where we don't have to touch something, like gravitational forces, electrostatic forces, and is magnetic on there, magnetic. So those are our non-contact forces. So have a little think about those as well. Now, this is one of those things where people tell me, I can't learn this. I can't learn Newton's 3rd law. How can I learn that? It's actually a really easy idea. It's simply that if you push on one thing, you get an equal and opposite reaction. Okay, so if you have 2 objects together, they exert an equal and opposite force on each other. Let's think about when you stand on a skateboard. If you stand on a skateboard and you push against a wall, you go in the opposite direction to pushing on the wall because you have an equal and opposite reaction. You push on the wall, it pushes you back, and you go in the other direction. You try and get out of a boat and you put one foot on the side and the other one pushes backwards and the boat disappears because you get an equal and opposite reaction. If you're towing something, you pull that way and it tries to pull you back. You can feel it doing that if you're trying to tow something. Equal and opposite reactions. That's all it is, Newton's 3rd law. It's just a description of those ideas. It actually comes down to things that are a little bit less obvious. If a book is sitting on a table If that book doesn't fall to the floor, even though gravity is pulling it down, the table must be holding it up with the same amount of force. Otherwise, it would fall on the floor. So we have equal and opposite reactions, sometimes from things that aren't moving. That's how they're kept still. For example, if you're sitting on a chair now, the fact that you're not on the floor is because there is an equal and opposite reaction from your chair, even though gravity is trying to pull you down, just as hard as if you jumped out of an aeroplane. Where we draw these arrows on objects, we call those free body diagrams. So where we're drawing arrows that show the forces on something, it's called a free body diagram. So if in your exam you see, label this free body diagram, they mean label this diagram with arrows. If they say draw a free body diagram, they mean draw arrows on it. That's all they're talking about. There's nothing more complicated than that. That's everything you need to revise for this quiz. That is the whole lot. So let me recap. Learn some units. They're important. Learn waves, transverse, longitudinal, label a wave, and if you can, the wave equation. Okay, fantastic. That's section 1. Section 2 is talking about magnets. The words that go with magnets like permanent and induce, repel and attract, and electromagnets. What are they? How can we make them stronger? Remember the word induce. We induce a magnetic field. We don't make it. Very important. Then we talk about forces. The units of force, contact forces and non-contact forces, Newton's third law, free body diagrams, and that relates to vectors and scalars, because if we can draw an arrow, it means we're drawing vectors. So free body diagrams have vectors in them. If you can remember all of those things, you're going to find the quiz really easy. We're not using it to try and catch you out. We're not using it to set you. We're not using it for anything else. This is for you to practice. Am I able to revise things? So you need to go away and revise. And by the end of today, that quiz will appear for you in your classroom. It's entirely multiple choice. You will get the mark at the end of it. It's just, can I remember those things? That's all there is to it. Now, we don't have the opportunity for you to ask questions because somehow I don't have that on here. So that is the end of this webinar. And you can now